Okay, so now we'll look at some code examples, but any questions so far? Okay. Okay, so let's look at our first code example here. It'll be somewhat similar to this, but we'll have a little bit more going on. Okay. So here, what we're doing is we're working off of an array of integers. And the goal is to be able to do some basic reading and writing with the file using this array. So we have an array here of int type with these 5 values. And then the name of the file that we're working with is called numbers.dat. And we open the file with these 3 flag sets, so binary, input, and output. And we could have also done, like, for example, fstream f object semicolon and then f object dot open, or we can open the file just at the same time that we create the object. But we're setting those 3 flags, input, output, and binary. Here at the beginning, we checked just to make sure that the file was able to open. One way to do that is by calling this function fail. So if we failed to open the file, that would return true. But assuming we were able to successfully open it, then what happens here, you'll notice, is we have just, and this isn't, we're not in a loop yet or anything like that. We just have a single call to the write function. So f object dot write, and then we have the, like we talked about before, the reinterpret cast char star. Notice here we're talking about the array though, right? ARR. So that's already an address, so there's no ampersand there, but cast that from type int star to char star. And then the second argument is just size of, and then the name of the array, which is going to give us the total number of bytes in that array. And then what we did is we did a seek G after the write. So what's going to happen here is we open this file, and based on the flags that we set here, we're going to start at the beginning of the file. So the thing that we're writing here is going at the very beginning of the file, right? Regardless of what already, might be there. So after that write operation, what we're doing is we're seeking, right? We're saying go back, right? Go back to the beginning of the file, and then we're doing a read into the other array, which has the same size as ARR. So ARR2 has the same size. So we're reading that, and then after that, we have a for loop that's supposed to print out all the elements in ARR2. So the idea is that we're trying to make ARR2 a copy essentially of ARR by first writing the contents of ARR to the binary file, and then reading from the binary file and putting that into ARR2. So you'll notice the way that we did that was we wrote to the beginning of the file. Here we needed to move the file position back to the beginning because we previously changed the file position, when we did the write call, but set it back to the beginning and then read now that we're back to the beginning. And you'll notice here that since we're wanting to go specifically to the beginning, we're just putting 0 for the first argument here. And then from there, just print everything out. But see, one thing that we're seeing here, again, was that we did not have to individually, right? We did not have to individually call write for each separate location in the array, or individually call read for each location in the array. Because we're doing the whole array in one go here, right, with this statement. And likewise, we're doing the whole array here in one go with one read statement. And the reason why that's possible, though, is because of the fact that the array itself is stored contiguously as one big block in memory. So it follows that as long as we specify the total number of bytes in the array, and of course we start relative to the beginning of the array, then that's going to process the entire array, whether it's a read operation or a write operation. So that's one of the convenient things here, is that we don't need a loop to do that in the case of the array, right? Just do the whole thing in one go. And then down here, again, we're just kind of testing out a few other things. So at this point, we've built the second array from the first array with the help of that binary file. Here, we're wanting to seek to basically the third position in the array. So we're doing 2 times size of int, similar to the Word examples from the Word document. Okay. Oh. Yeah, with the byte, yeah, good question about erasing or not erasing. It depends what we're doing. In general, it certainly is possible to have a persistent file that you can maintain over a period of time, meaning that the old contents are not lost. It really depends upon how you open the file and where you start reading or writing to. Now here in this case, with the way this works, we are always starting the write at the beginning, so that is going to overwrite, whatever was previously there. I mean, of course, we're running, in this case, this is with hard-coded data values, so it's just writing over itself with the same values. But I mean, what you can do there is you can, for example, seek to the end of the file and write the new record there if you don't want to erase what's already there. And in fact, that's also, depending upon what you want to do, but there's also the flag APP for append, which basically means that you're always going to write at the end of the file. So when you, we don't have that here, but if you have the APP flag, then essentially whenever you do a write call, before the write call, you do a implicit call to seeking to the end of the file. So meaning that the only place that you could write is the end of the file. You could read anywhere, but the only place that you could write would be the end of the file, which means that you're not able to change data that's already there. There's also another flag called trunk for truncate, which will force it to clear. If the file already had contents, would force it to delete everything. Here we're not doing either of those flags, right? So yeah, we can persist the file, but we also are overwriting at the very beginning too, with the way that we set up write here. So build array 2, print array 2 out, and then what we did, just again, kind of testing a few things out, seek to, and this is seek p, seek to the third number, right, in the file. So 2 times size of int, since we're storing integers, and then seek relative to the beginning, iOS BEG, and then a little statement here that says currently at byte, and then, I mean, tell P and tell G both are going to give the same thing there. And then write, call to write. And in this case, we're just referring to X, right? So reinterpret cache char star address of X. And then notice here we're saying size of int. You could have also said size of X, because X is just this variable here. But so the idea is that we're wanting to overwrite one of the values that was originally coming from the array with this single integer variable that has 99. Because remember, we previously built the file with the array values from ARR. Now we're saying I want to change that one, the third number in the file. So the 20. I want to change that to 99 with this right here. So seek to the third position, which really has to be 2 times the size of an integer relative to the beginning, and then write x, address of x, and then size of integer. And then here we just did another seek, again, just seeking back to the beginning, and then another thing that's going to tell us, which byte we're at in the file. And then after doing that, what we did is we did another read here again with ARR2, and then we loop through ARR2. So we're again repopulating ARR2 with the new state of the file, right? The new contents of the file, and then printing that out. So the idea being that here we were wanting to change that one value to the 99, right? That was coming from X. So again, just testing out, some of the basic concepts here. And then the file that we're running this through is called numbers.dat, just a dat data file. And then in this case, when we run it, we're just going to get this kind of output here. So first, we loop through ARR2 after building it from the binary file, which itself was built from the first array. So we printed out the values 10, 15, 20, right, with that first loop. And then we have those calls to things like the telg and the telp. The first one, remember we were seeking to the third number, which would be at byte number 8. And we printed it out twice since we use both telg and telp. So currently at byte 8 and then 8 again in the file. So just printing that byte position out twice. Then we seeked back again to the beginning with seek G. We seeked back to the beginning with 0 and iOS begin. And then remember that was where we did the statement, the write statement with X, where we said 2 times size of integer. So now we're changing that third number in the file, which originally was 20 to 99. And so now when we read again from the file into ARR2, we're overwriting really each location in the array, but the one that changes really in value is the third one from 20 to 99. So we're repopulating the array a second time from the new state of the file. So that, the 10 overwrites the 10, the 15 overwrites the 15, but then that 99 overwrites the 20 there. So again, one of the nice things here also is that because of the way that arrays work, we were able to just do, one read or one write to deal with the entire array, right? We didn't have to separately deal with each index, given the fact that the whole thing itself is stored back to back in memory. And now again, the file itself, right, because it is a binary file, if we actually look at the file, right, we're not going to necessarily see what we might consider to be meaningful stuff in the file. So, but we can confirm that it's working correctly here through the program, right? But actually, just opening the file is not really a way to try and confirm what it's storing. So we do have to have some knowledge of the file, right, in that sense, because again here, and again, this was just run in Visual Studio where the file itself was in the same directory, right? So same directory as the CPP file, like how you did in your previous assignments. But just to go real quickly here to the file, this is what we're going to see, right? And that's it. So again, looking at the file itself, you're not going to be able to really interpret the data just by opening the file in something like Notepad, but we can interpret it by using things like the read and the seeks and so forth in the program to confirm what we know should be the case in terms of the file. So here we're kind of seeing, some random stuff like, those symbols and then the C there. So it's not, on the surface, it doesn't really look meaningful, but then we can confirm it through the program. So in general, when you open a file like this, it's, being processed in binary mode, you're not going to just see all the data in the way that you would with a standard text file that's being processed in ASCII text mode. So this is what, if you open up this numbers.dat file with what we've already done, this is what it's going to look like, right? And we clearly are not, seeing things like the number 10 and the 15 and so forth. But nonetheless, we know that it's there because we saw that happening when we actually read through it and saw it in terms of the console output in the program. But that just gives you an idea of what's going to, what things you might see if you actually open up, right, the binary file in something like Notepad here. It's not really a reliable way to try and confirm, what's actually in the file itself. So we do need to confirm those kind of things through the program itself, in other words. But that's gives you an idea of how this is going to work, at least with arrays. And so let me switch back here for a moment. But we'll also look at what you can do with structures, because that's going to come up in your assignment. So we'll look at the next example we'll look at. It's going to involve structures and actually linked lists too. And it'll be a little bit different than this one. But again, here we saw the basic idea in terms of how this would work out with an array. And again, it really was convenient that we were able to do things off of really a single write or read for the entire array. So certainly, I mean, you could do things like a loop and then, instead of saying like, size of ARR, size of int, and then refer to just an individual element from the array, cast that to type char star and go one at a time. But it's really not necessary to do that, since the array itself is just one big block in memory. So we were able to take a direct advantage of that with this program here. And again, we saw things like, good usage of seek. So here again, we wanted to change the third number in the file to 99 really. So the index number here was 2 multiplied by the size of integer. So seek to the third, where the third number starts, and then write the value of x, which was 99, at that exact byte position within the file. And then again, we seeked back to the beginning after doing that, and then read the entire file contents again back into AR2. And then we were able, with that final for loop, print out the new state of the array with that third value now being, the 99 instead of the 20 that originally was. Okay, so any questions on that so far? Okay, but let's think now about structures and linked lists, because that is going to be a little bit different, because we know that the nodes in the linked list itself are not stored together in memory. The fields within a single structure object are together, like the name, ID number, letter grade, test score, next pointer, for example, but across different objects, right? We know that the nodes in general are not stored contiguously. So we'll have to do a little bit more, but we can still do things like certainly like combine a binary file with a linked list, right? So build a linked list from the contents of the binary file. It'll just be a little bit more involved compared to what we did here with an array. But so we'll look at that example next. And what we're going to do here is we're going to make a slight change to the implementation of the structure, because now that we have an idea of how this whole process with binary files works, and we said that everything comes down to the individual byte level, but something like type string is really a problem, right? Because a string is like a vector, right? They're both, string and vector are both dynamic arrays, but whereas a vector can store any type, which is why we specify the type in the angular brackets. A string is always storing characters, right? So it's a dynamic array of characters. But in terms of a binary file, that's a problem because it means that not every student object would not be the same size. And that's going to be a big problem when we talk about processing the file, because we should in general be able to seek to a particular record with student information and, for example, only read that record. But that's only going to work if we can count on the fact that each student record is going to take up the exact same amount of memory. So instead of having the name as a string type, we're going to make it a fixed size array, and we're going to make it an array of characters rather than a string object. So again, there'll be some slight differences compared to when we last saw this with our linked list project, but a lot of it will be the same. So to start off here, again, this is what we changed. So instead of this being a string, now it's an array of characters with a fixed size. So again, very, very important, because every single student object needs to take up the exact same amount of memory. So that way, if we provide offset for the byte number, we can always go to that byte number, just in the same way that we did with the array of integers. Because remember, if we're going to do things like prompt the user for, for example, for input here, then you could take that number that they enter and then multiply it by the size of, for example, student object to control to which location within the file that you seek to, and only read in that one student object. But that's only going to work if all the student objects take up the exact same amount of memory. So, we want to avoid things like type string here, right? We want to keep everything at a fixed size. So we're going to make this a character array. And now we're imposing a maximum here. So we're saying that, in general, 30 characters should be enough for a name. And it's perfectly fine if the name is less than that. The main point is that in terms of memory, the same amount of memory is taken up all the time. And so we have that. We have the usual fields from before, the ID number, letter grade, test score, along with the next pointer. In the beginning here, we open this file, this time called students.dat, with input, output, and binary. And then here we're going to start by building up the binary or the linked list here first. So what we're going to do is we're going to build the linked list with some hard-coded values. We're going to write those values to the binary file. And then we're going to actually, once the file's been built, we're going to read from the file in reverse order through seeks, and then read that back into the linked list, right? So the end effect of all that is that we're going to really reverse the order of the contents of the linked list, right? So again, we're going to build the linked list with some values. When that's done, we're going to loop through all the nodes in the linked list, write them one by one to the binary file. And then when the binary file has been built, we're going to read through the file in reverse order through several calls to seek, right? And then in essence, read it back in reverse order into the linked list. So the end effect is that when we loop through the linked list the second time, everything's going to show up in the reverse order compared to the first time. Actually, do that here. So similar to before, we start by creating an object here, and now it's a little bit different though, because it's not a string, right? It's an actual array of characters. So what we're doing is we're individually setting each character one by one. So the first name here is James. And then after that, the other important thing here, so that way when we print it out, we're not going to get any extra garbage printed out, is after the name itself is finished, we're going to put what's called the null terminator character at the end of our character array. So that way, if we do a, like a cout statement with name, it'll go up only until the null terminator, and it won't print out a bunch of garbage values for the unused positions within the array, because the array itself is 30, but in general, right, the name, of course, might be much less than 30 characters. Like a name like James, for example, is really only 5 characters. But we don't want to print out something like James and then a bunch of garbage, values after that. So the way that we can fix that is just to, whenever we're done with the name itself, the next index in the character array is going to be that null terminator. Now with a string object, we don't really have to worry about that because of the way the string class works. But when you're dealing with an actual character array, you want to think about these issues and make sure that the string or the character array ends with a null terminator. And we're using the bracket notation here, but then you could also use the this notation too with, for example, new node arrow name +1 with the star on the outside, or you can use the bracket notation here as well. But we're populating each letter one by one, and then that null terminator here. And then we're setting the ID number, letter grade, test score. And now a lot of this is similar to what we did before. We're building some hard-coded linked list nodes and connecting them together. And so that part's going to be the same as what we did when we first started talking about linked list. So for example, head equals the first node, create the second node Dave, end it with null terminator, set the other fields, connect the first node to the second node, right? That part's the same as before. Create the third node, which is going to be Amber. Make sure we end it with null terminator, set the other fields, right? Connect the second node to the third node, and so forth here. This is the Sarah node, then connect it, and then this is the Bob node, and then we're going to connect that. So most of that, again, is the same as what we did before in terms of how it creating the 5 nodes and then, connecting them together. But again, a little bit different now that it's a character array rather than a string. So we just individually set each location in that character array, and then again, ended it with a null terminator. Now, but let's get to the next part here, because this is where the binary file aspect is going to come into play. So what we're doing here is similar to our traversal loop. So at this point, we've built the linked list up. We're going to loop until PTR is not null pointer, print out everything in the node, and then write. So we're writing an entire structure object to the binary file. But notice what we did here for the second argument to write. Size of student. So the idea is that it's all the same in the end. It doesn't matter if you're working with a character, with an integer, with a double, with a student structure object. It's all the same, right? In the end, everything is ones and zeros, right? Everything is just binary in the end. But we do have to distinguish the amount, right? How much are we writing here? But fortunately, if we apply the size of operator to student, right, that's going to give us the exact number of bytes that a student object takes up in memory. And since we aren't using anything that's dynamic like a string object, we also furthermore know that every single student object takes up the exact same amount of memory. So we're good there. Now, again, we can't, like, because this is a linked list now, we can't just write the whole linked list in one go, because the nodes in the linked list, right, are not stored together in memory. So there's no way to, to grab all the bytes for all the nodes and do one big write operation. But we can at least do all the fields, right, for one student object in one go. So what we're doing here is, if we look at what's happening with this call to write, notice the first call here is we have that familiar reinterpret cast char star, what we're casting is PTR, right? But PTR is pointing at either, it's always pointing at either null or one of our linked list nodes. At the beginning, PTR is pointing at the first node. So because PTR itself has type student star, right? Address of a student object or pointer to a student object, but we're going to go ahead and cast that to type char star, pointer or to a character, address of a character. At the same time, the number of bytes that we're writing is the size of a single student object. So notice in particular here that even with the structure object, we don't have to individually write, the name and the ID number and the letter grade and the test score. We don't have to write those separately. We can write the entire object right in one go, similar to how we wrote or read an entire array in one go, because we know that within a single object, all the fields, right? All the fields are stored back to back in memory. So we're taking direct advantage of that here. So the idea is that the loop here is looping over each node in the linked list, similar to our traversal algorithm from before. And what we're doing is whatever node that PTR is currently pointing at, we're going to take all that information in that object, everything from the name even down to the next pointer. We're going to write all that to the binary file. So we're storing all this information from the linked list now into the binary file, and we're doing it by just repeatedly calling this write function. So this prints everything out on the console screen like before, and then write that entire node to binary file. So can't do the whole list in one go, but we at least can do one node itself in one go, which is still good. So just one call to write per loop iteration. Again, that's writing the entire object, whatever PTR is pointing at. So yeah, size of student is fine here. Or something like size of dereference PTR is also fine. And then move PTR up in the usual way, right, with PTR arrow next. So now all that is in the binary file, right? Everything that we established here. So if you think about the file from start to finish, of course we know it's ones and zeros, but you have James, right? You have, and that's really 30 bytes because that was the size of the character array. Then you have, for example, the 4 bytes for the ID number of the integer. You have a byte for the letter grade, usually about 8 bytes for the test score. And then the next pointer itself is usually 4 bytes, right? Meaning the same size as the integer. And then right after that, we have the next node, right? Where we have Dave, the ID number, letter grade, test score, next pointer. So all that, right? All that is now being stored in the binary file. So now the second loop, the follow-up loop, is going to be essentially rebuilding the linked list, the same physical nodes, because we're not like creating new nodes and creating new links and all that. But in essence, what we're doing is we're rebuilding the linked list in a different order now from the binary file that we just built with the previous loop that just finished. So now we're going to print everything out in reverse. And there's a little bit of extra detail here as well. Because in general, we have to be careful about the next pointer in particular. But what we're doing is we reset PTR back to the beginning of the linked list. We're going to loop until null pointer. And now we have a seek G and a read. So we're pairing those two up. We also have this variable I. So let's look at I here. I was initialized to, so num of nodes was 5, because that's how many nodes we have in this list. And then I is 1 less than that, right? So I is num of nodes minus 1 or 4 really. And so in the first iteration, I is going to have the value 4. And then we're multiplying that by size of student. And then we're doing IOS begin. So putting it together here, the idea is that we're wanting to seek to the last student record in the file. Because, for example, if we just for a moment, if we were talking about characters, let's say, right, and if we had 5 character values in our file, then we know that the indexes would be 0 for the first character, 1 for the second, up to 4 for the fifth one, right? So just like an array, we say with an array, right, the biggest one is size minus 1, right? The biggest index is size minus 1. Well, it's a similar idea with the binary file. Except here it really would be not necessarily size minus 1, but rather size minus, right, the number of bytes for a single record. When we say record, that just means, in this case, it means the student object, which has all 5 fields from the name down to the next pointer, right? So what we're doing then is we're multiplying 4, actually, since there's 5 records total, 4 by the total size of a student object. So that's going to take us to where the last, right, the last of those student objects are in the file. So in particular, it's going to take us to where this Bob, right, this Bob object is in the binary file. If we put in, for example, 3, then it would take you to the second to last. If you put in, 0, of course, it would take you to the beginning. So I controls which one we're getting on each loop iteration. So on the first iteration, in other words, go to the last, right, the last record. So not the end of the file, but the last record, because there's a difference between those two things, which is also why we're saying 4 rather than 5 here for I's value. But go to the last record, go to the Bob record, seek there, and then follow that up with a read statement. So now what we've just done is we've read that in, right? We've read that in. Into PTR. Now, there's a couple other things going on because, we need to be a little bit careful with things like the next pointer. Especially in a general sense, if we're like especially if we were creating like a new linked list. So because the next pointer is storing an address, and especially since a binary file might persist over a period of time, right? In general, you're not going to want to do things like take, an address from a file and put that into one of your pointers, right? Because certainly in general, if we run this program over and over, right, the linked list could be at, different locations in memory. So usually we're not going to be doing stuff like that. Now, taking in the actual data values, like the name, the ID number, the letter grade, and plugging that into the node, right? That's fine. We shouldn't really be getting the value of the pointer though from a file, right? Because that in general, that's not reliable, right? We can't just assume that that's going to be appropriate for the given linked list that we're working with. So what we're doing here is we're actually saving the value of PTR arrow next before the read operation. We're saving, meaning we're saving the address stored in the next pointer in temp, and then we're restoring that after the read operation. Because what's going to happen, when you do the read operation, is it's going to read all 5 fields, right, including the address from the next pointer that was previously written to the file with this write call. But we're just saying, in effect, don't actually use that, right? Just use what was already there. So we're still going to take in everything else, like the name, the ID number, the letter grade, and the test score, but we're not going to actually take in, really, in the end, the value of that pointer, right, from there. Because in general, that would be a big problem, right? Because file could persist for a long time, but in general, certainly the linked list, could change, right? Each time you run the program could be at a different location. So we don't really want to be doing that kind of thing. So just go ahead and save the next pointer in temp, and then again, when you do the read itself, it is gonna change the next pointer because it's gonna come from the file. But then we're just gonna immediately restore next to what temp was storing. So in the end, in effect, right, we're basically, the end result is that we're reading everything, but we're not actually taking really whatever was in the field for the next pointer from the binary file. But we are taking everything else there. So you do want to be very careful about things like that. So here we don't really want to be, because values are one thing, but you don't want to be doing things like getting a pointer's value from a binary file, because in general, that address is not going to be reliable in general over the long haul, right? So that's something we definitely don't want to really do. So go ahead and restore that next pointer, and then print everything out. But the result of all this is that when we go through here and we print this out on each loop iteration, the end effect of all this is that the data values in the linked list have now been reversed. So now first node, we're going to see, for example, on the first iteration, we're now going to see the Bob node, right, which was the original last node, and so on and so forth. So, and again, it comes down to how we're using I here, because on the first iteration, I is 4. So, because in terms of, if we think of like array indexes, that would be the size -1, right, the last index. So that's multiplied by the number of bytes that's taken up by a student object. But at the same time, we also decrement I on each loop iteration. So 4 on the first loop iteration, 3 on the second, and then 2, right, then 1, then 0. So we're reading from the file basically in reverse order. So the idea is we're controlling that by seeking to the right spot on each loop iteration. So seeking to the last record on the first loop iteration, seeking to the second to last on the second iteration, and the third to last, right, and so on and so forth in that order. And then reading that into the object with the read statement. But again, very, 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 very important here is preserving that next pointer. We don't want that to actually be coming from the file, really. So, but that's a simple fix here. Again, just save before the read. So this needs to be before the read statement. Save whatever next is already storing into temp, and then after the read, go ahead and take temp's value and plug that back into the next pointer. And then we're not going to have any problems there with corrupting the next pointer, potentially over time. So, and then that's it. So that's how we combined here linked list with our binary file. So, but again, pointers, right, really should never, should never be getting their values from a file. So ways that you could handle this would be to, for example, individually read only the first four fields, right? But then you'd have to do, for example, 4 calls to read for the name field, ID number and all that. Or you can just simply do a save and restore before and after the read with PTR's next pointer. So either way is going to work here. So we just went with that approach. So that way we only had to do, one read operation. Now, of course, what we do here has to match up with what we did in the write loop, right? So if we're writing all the bytes, including the bytes for the next pointer, then we need to do the same thing when we read it, right? Because that's how big our structure is. On the other hand, if we originally, if we did separate write calls for the first 4 fields, then the corresponding logic here would be 4 read calls, but the two should match up, right? So that way we're reading the right number of bytes with each read operation in either case. But here we just went with the approach of saving and restoring the next pointer. So that's not really going to be coming from the file in the end, but everything else is coming from the file. And so when we run through this and print it out, the end result is that the second time, the names, all the fields are going to show up in reverse order, right? The name, the ID number, and so forth, because of what we're doing here with this seek function call. That's the key to making this work, right? Just seeking to the right spot on each loop iteration, and then reading that back into your current node, and then printing out, right, each of the 4 fields like we did in the previous loop iteration. Okay. And then again, this time we're working with, in this case, it's called students.dat. So let's go ahead and run this. Hold on here, let me see. Okay. So here the first thing is we print out the names in forward order. So because we built that, those nodes with hard-coded values in the beginning. So we first built up the list, and then we built the file. So we have the names in forward order, and then we have that second loop here where we now show them all in reverse order. So first time we have James, Dave, Amber, Sarah, Bob, and now we have Bob, Sarah, Amber, Dave, James. But the way in which we reverse them in this case was really through the binary file. So we first built the hard-coded nodes, wrote them in order with that first loop to the binary file. But then in the second loop, the key was that we seeked to the right spot on each loop iteration and only grab that. So again, on the first loop iteration, you notice that we're getting the Bob node here. But remember what we did was in that call to seek G, we said the value of that I variable, which we started at 4, because we think of it like an array, right? That would be the index of the last one. If there's 5 nodes, the index would be 4, the last one. But we had to also multiply it, right? That 4, we had to multiply it by the size of a single student object, right? Because just like how we talked about in the Word document when we were talking about how the file might be storing integers, and we said that the first one was at byte, byte 0 to 3, and then byte 4 to 7. Well, it's the exact same idea here, except now we're talking about the size of a student object. So if, let's say, maybe it's 40 bytes, right? And I'm just kind of throwing a number out there, but let's just say when you add everything up, it's 40 bytes for a student object. We have to take that into account, right, when we talk about things like seeking. So you have to take in what we can think of as your index number, which is what I is, but then we still have to multiply that by the number of bytes. So on the first loop iteration, that's how we're seeking to where the Bob record in the binary file starts. And then on the second iteration, I is going to be 3 since we decrement it. So now we're doing 3 times size of student, which is going to take us to the second to last, or the 4th record, which is the Sarah record. And then on the next iteration where we get Amber, it's going to be 2, right? 2 times size of students. So we're going to get to the 3rd. And then on the 4th iteration, I is going to be 1 times size of student. So we're going to get to the 2nd record. And then on the last iteration, it's going to be 0 times size of record. So just 0. And then we're going to seek to the beginning and we're going to get the 1st record. So that's how we were able to ultimately rebuild the list or repopulate the list with everything now in reverse order. So we're seeing how all these things can be combined together to really handle, whatever situation comes up that we need to handle here. So that's, again, a little bit more involved example, but now we're even seeing how linked lists can be potentially combined with binary files. So it's just a matter of thinking about how these things are going to come together, like your seeks and your reads and your writes. And then in this case, working that in also with your underlying linked list structure. Because in your assignment this week, you're going to be doing some similar things. So we'll put these code examples up so you can refer to them. But as part of it, you're going to be eventually doing things like building a little linked list from your binary file. But now we're seeing an idea of how that's going to work out here. Okay.